Picture yourself drifting alone in the infinite expanse between the stars, enveloped by a profound and absolute silence. There are no shimmering galaxies in view, no familiar planets to orient yourself, just an endless, velvety blackness that seems to swallow both light and sound. It's a scene that has captivated dreamers and scientists alike. But behind that breathtaking emptiness lies a reality far more unsettling. What appears to be void is, in fact, one of the most treacherous environments humanity could ever encounter. A realm where danger doesn't always announce itself with flashing lights or roaring sounds, but instead waits silently in the absence of everything we consider safe. We often think of space as a grand, beautiful nothingness, a blank canvas for stars and nebulas, but that emptiness is an illusion. Those dark patches between celestial bodies are not truly empty. They're filled with invisible forces and phenomena that defy our everyday understanding of reality. From deadly cosmic radiation that can penetrate the sturdiest of shields to gravitational tides that could pull a spacecraft silently off course, the void is anything but passive. It challenges our technology, our biology, and even our psychology in ways we are only beginning to grasp. And as we set our sights on longer, deeper journeys into the cosmos, to Mars, to the outer solar system, and beyond, understanding these hidden threats isn't just scientific curiosity, it's a matter of survival. In this video, we're venturing into these vast and silent realms to uncover why the emptiest parts of space might also be the most dangerous. We'll explore how radiation from distant supernova tears through the void, how the crushing isolation preys on the human mind, and how something as simple as navigating without landmarks becomes a life or death puzzle. This isn't just a story about space, it's about the limits of human endurance and ingenuity in the face of the unknown. So settle in, open your mind to the mysteries ahead, and join us as we reveal why, in the grand theater of the cosmos, what you can't see might be what you should fear the most. But what exactly do we mean when we call a region of space empty? It's a term that feels intuitive, suggesting a complete and total absence of anything at all. Yet in the cosmic sense, this idea is perhaps one of the most profound illusions the universe presents. The black, starless stretches between galaxies, the vast gulfs between star systems within our own galaxy, these are not true voids in the absolute sense. They are not nothing. Instead, they are realms of extreme and almost unimaginable scarcity. To put it in perspective, the air we breathe here on Earth contains about 10 quintillion molecules in a single cubic centimeter. In the deepest, darkest intergalactic space, that same volume might hold just a single atom, or perhaps even less. It is a vacuum so perfect that our best laboratories on Earth can only dream of replicating it, yet it is still not entirely empty. This near-nothingness is teeming with invisible activity. Besides those sparse atoms, mostly hydrogen, left over from the Big Bang, this so-called emptiness is permeated by a constant rain of high-energy particles, cosmic rays hurtling across the universe at nearly the speed of light. It is flooded with the faint, ancient glow of radiation from the birth of the cosmos, the cosmic microwave background. And perhaps most mysteriously, it is shaped and structured by the gravitational influence of dark matter, an unseen substance that we cannot directly observe, but whose presence we know holds galaxies together. Then there's dark energy, an even more enigmatic force infusing this space and driving the accelerated expansion of the universe itself. So when we label these regions as empty, we are really only commenting on the absence of the things we can easily see and measure. We are focusing on the lack of stars and planets, ignoring the subtle, complex soup of physics that fills every cubic inch. This is a critical distinction because it redefines the very nature of the challenge. The danger of these zones isn't just about what isn't there, the lack of air, the lack of warmth, the lack of refuge. The greater peril often lies in what is there, unseen and unheard. This invisible landscape of forces and particles is what transforms a passive journey through nothing into an active navigation through a minefield of potential hazards. Understanding that emptiness is an illusion is the essential first step in respecting the true nature of deep space and preparing for the very real risks hidden within its dark embrace. And it is within this unseen landscape that we encounter one of the most formidable and insidious threats of deep space, cosmic radiation. Imagine an endless, invisible hailstorm of atomic fragments, each one a bullet traveling at nearly the speed of light. These are cosmic rays, and they originate from the most violent events in the universe, the cataclysmic explosions of supernova, the furious jets erupting from black holes, and the tumultuous surfaces of distant stars. Here on Earth, we are blissfully unaware of this constant bombardment. Our planet's sturdy magnetic field acts like a powerful shield, deflecting the vast majority of these particles away from the surface, while our thick atmosphere serves as a protective blanket, absorbing and dissipating the energy of those few that make it through. We are, in effect, living in a very well-fortified castle, but venture outside those walls into the deep void between worlds, and that protection vanishes entirely. An astronaut floating in interplanetary space is utterly exposed, their spacecraft offering only a flimsy defense against such high-energy assault. These aren't just simple particles, they are atomic nuclei stripped of their electrons, hurtling through space with immense energy. When they slam into the hull of a ship, they can create a secondary shower of even more particles, a dangerous splash effect that turns the ship's own structure into a source of additional radiation. This is the cruel paradox of the void. The very emptiness that defines it allows these particles to travel unimpeded across galactic distances, carrying their destructive potential directly to anyone or anything in their path. The biological damage this radiation inflicts is profound and deeply concerning for long-duration missions. When these high-energy particles tear through the human body, they don't just pass through cleanly like a tiny bullet. They leave a trail of destruction in their wake, shredding DNA molecules, breaking chemical bonds within cells, and creating highly reactive free radicals that can cause further damage long after the initial impact. This cellular chaos significantly increases the lifetime risk of developing various cancers, a serious enough problem on its own, but the effects are even more immediate and alarming. Studies have shown that exposure to cosmic radiation can lead to cognitive deficits, impairing memory and problem-solving skills, a terrifying prospect for a crew that needs to make split-second, life-or-death decisions millions of miles from home. There is also emerging evidence that it can accelerate the development of cataracts and even cause damage to the cardiovascular system, effectively weakening the body from the inside out. This is why the emptiness of space so dramatically amplifies the threat. In low Earth orbit, aboard the International Space Station, astronauts still receive a measure of protection from Earth's magnetosphere, though their exposure is still many times higher than on the ground. A journey to Mars, however, or beyond, would plunge a crew directly into the heart of this particle storm for months or even years at a time with no natural sanctuary in sight. The sheer scale of the void means there is nowhere to hide, no planet to duck behind for a significant portion of the voyage. Shielding against it presents an enormous engineering challenge. Lead or other traditional materials would be far too heavy, and might even make the problem worse by generating more secondary particles. Scientists are exploring more elegant solutions, like using lightweight hydrogen-rich materials or even creating artificial magnetic fields around the spacecraft, but these technologies are still in their infancy. The silent, empty cosmos, it turns out, is filled with an invisible rain that poses one of the most fundamental challenges to our dreams of walking among the stars. While the invisible barrage of cosmic radiation attacks the body on a cellular level, there is another, more persistent force at work in the void that reshapes the human form from the inside out, the relentless and unyielding pull of microgravity. Or rather, the profound lack of it. Here on Earth, gravity is the constant, unseen workout partner for our entire lives. It provides the resistance that keeps our muscles toned, our bones dense and strong, and our cardiovascular system constantly pumping blood upward against a downward force. The moment an astronaut enters the weightless environment of space, that foundational force simply vanishes. The body, which has spent a lifetime adapting to a 1G environment, suddenly receives a signal that its work is done. The consequences of this biological misunderstanding are both rapid and severe, turning the comfortable emptiness of a spacecraft into a chamber of gradual physical decline. One of the most immediate and visually apparent effects is the loss of muscle mass and strength, a condition known as muscle atrophy. Without the need to stand, walk, or even lift a limb against gravity, the muscles begin to weaken and waste away at an alarming rate. The anti-gravity muscles in the calves, thighs, back, and neck, the very muscles that keep us upright, are hit the hardest. Astronauts can lose up to 20% of their muscle mass in missions lasting just 5 to 11 days, and that deterioration only accelerates on longer journeys. This isn't merely about losing physical strength for tasks like spacewalks or lifting equipment. It's a fundamental deconditioning that poses a serious risk for when they eventually return to a world with gravity. A weakened crew would struggle to perform emergency procedures upon re-entry, to evacuate a spacecraft quickly, or even to stand upright on a new planetary surface like Mars. Perhaps even more concerning than muscle loss is the silent leaching of minerals from the skeleton. Our bones are not static structures. They are living tissue in a constant state of renewal, with cells called osteoblasts building new bone and osteoclasts breaking down old bone. On Earth, this process is in equilibrium, stimulated by the mechanical stress of bearing weight. In microgravity, that stress disappears, the balance is shattered, and the body, in its ruthless efficiency, decides that maintaining strong bones is no longer a priority. The osteoclasts go into overdrive, resorbing bone material, while the osteoblasts slow their work to a crawl. The result is a condition similar to osteoporosis, but occurring at a rate up to 10 times faster. Astronauts can lose between 1 and 2% of their bone mass every month, particularly in the weight-bearing bones of the hips, spines, and legs. This loss of calcium doesn't just weaken the skeleton, making it more prone to fractures. It also floods the bloodstream, increasing the risk of painful kidney stones, a medical emergency that would be incredibly difficult to treat millions of miles from Earth. This systemic shift impacts the very river of life within the body, the cardiovascular system. Our hearts are powerful pumps designed to fight gravity, pushing blood upward to the brain. In microgravity, fluids shift toward the upper body. The face becomes puffy, the legs thin out, a phenomenon astronauts call bird legs, and the heart, no longer needing to work as hard, begins to weaken and lose muscle mass itself. It becomes smaller and less efficient. This deconditioning is so significant that upon return to gravity, astronauts often experience dizziness and fainting, a condition known as orthostatic intolerance, because their shrunken hearts and relaxed blood vessels struggle to push enough blood to the brain against the sudden return of a force they'd grown unaccustomed to. The emptiness of space, by removing the constant pressure of gravity, doesn't just create a temporary physical change. It triggers a deep physiological reprogramming that questions the very definition of human health. The body, in its adaptive wisdom, optimizes itself for a world without weight, becoming perfectly suited for an environment that is utterly alien to its evolutionary design and perilously ill-suited for any other. While the human body contends with the internal decay brought on by radiation and microgravity, the external environment of the void presents a more immediate and violent danger, a relentless and invisible shotgun blast of high-speed projectiles. It's a common misconception that traveling through the vast, empty stretches between planets is like sailing on a calm, empty ocean. In reality, it's more like navigating a minefield where the mines are often smaller than a grain of sand but hit with the force of a cannonball. This peril comes in two forms: the artificial clutter of human exploration, known as space debris, and the natural background noise of the cosmos, micrometeoroids. Humanity has been littering the orbital pathways around Earth for decades, leaving behind a swirling cloud of discarded history. This includes everything from spent rocket stages and defunct satellites to lost tools, flakes of paint, and even frozen coolant droplets. Each mission, each launch, adds to this growing shell of technological detritus. While the greatest concentration exists in low Earth orbit, this debris doesn't stay neatly contained. Over time, gravitational perturbations and solar radiation pressure can scatter fragments into higher, lonelier orbits, and even into the translunar space that future missions to the Moon and Mars must traverse. So even as a spacecraft ventures away from Earth, it's not truly leaving our mess behind. It's simply entering a region where the garbage is more spread out, but no less deadly. Then there are the natural inhabitants of the void, micrometeoroids. These are tiny fragments of rock and metal, often remnants from asteroid collisions or the dusty tails of comets, that have been wandering the solar system for billions of years. They are the true natives of the empty space we seek to cross. What makes both this human-made debris and these natural particles so extraordinarily dangerous is not their size but their speed. In the frictionless vacuum of space, objects are in constant, rapid motion. In low Earth orbit, the average impact speed is around 22,000 miles per hour. In the deeper void, where objects are moving on different orbital paths around the Sun, closing speeds can be far, far higher. At these velocities, kinetic energy becomes the great equalizer. A fleck of paint traveling at 10,000 miles per hour possesses enough energy to crack the thick glass of a space shuttle window. A metal sphere the size of a marble would hit with the explosive force of a hand grenade. An object the size of a softball could literally vaporize an entire spacecraft. This creates a terrifying engineering challenge. How do you armor a vessel against such threats without making it impossibly heavy? Modern spacecraft use something called a Whipple shield, a clever design involving outer layers of thin material designed to vaporize an incoming particle, spreading its energy out so that the inner hull can withstand the resulting cloud of gas. It's effective, but it's not perfect, and it adds significant mass. For larger objects, the only strategy is to see them coming and get out of the way. But that leads to the second, perhaps more insidious problem: detection. In the profound darkness of deep space, finding these objects is like trying to spot a single, unlit black marble from miles away against a perfectly black background. Ground-based radar is useless once you move beyond Earth's immediate vicinity. Onboard sensors have a very limited field of view and range. A spacecraft might only receive a few seconds of warning before an impact, if it receives any warning at all. This means that for much of a journey through the void, the crew is essentially traveling blind, placing their faith in probability and sheer luck. They are betting that the incredible vastness of the space around them will be enough to protect them from the incredibly dense energy of the particles within it. It's a high-stakes game of statistical chance, where a single encounter with a forgotten bolt or a wandering speck of cosmic dust could turn a mission of discovery into a silent, tragic footnote in history. A stark reminder that in the emptiness of space, sometimes the smallest things pose the very largest threats. While the physical threats of the void are formidable, they are challenges that can be quantified, measured, and engineered against. But what happens when the greatest danger isn't outside the spacecraft, but inside the human mind itself? The psychological toll of deep space travel presents a risk that is far more nebulous and, in many ways, far more difficult to defend against. Imagine the experience. You are part of a small crew, perhaps just a handful of people, sealed inside a metal can for months or even years. Outside your window, there is only an unbroken, infinite blackness. There are no sunrises, no passing clouds, no changing landscapes. The only sound is the constant, low hum of life support machinery, a sound that quickly fades into a maddening silence. You are further from home than any human has ever been, and the sheer scale of that distance is not just a number on a screen, it's a visceral, psychological weight. This is the reality of sensory deprivation and isolation in the void, and it is a perfect storm for mental health crises. The most immediate and profound effect is the complete removal of earthly sensory cues. Our brains are hardwired to process a constant, rich stream of information. The feeling of wind on our skin, the sound of birdsong, the sight of a horizon line, the subtle change in light from morning to night. These inputs aren't just pleasant background noise, they are essential anchors for our mental and emotional stability. They keep us grounded in reality and in time. In the depth of space, all of that vanishes. The view from the window, once the thrilling pinnacle of the journey, can become a source of deep anxiety, a stark reminder that you are suspended in an environment that is utterly hostile to your existence, with nothing but a thin hull separating you from oblivion. This can trigger what psychologists call break-off phenomenon, a dissociative state where individuals feel completely detached from Earth and humanity, as if they are floating away not just physically, but emotionally and existentially as well. This sensory starvation is compounded by a communication delay that grows longer with every mile traveled. A conversation with mission control or loved ones back on Earth becomes less like a chat and more like sending and receiving letters. A simple question might take 20 minutes to receive an answer. This lag eliminates the possibility of spontaneous, comforting conversation. There can be no sharing of a sudden thought, no quick joke to lighten the mood, no real-time comfort during a moment of fear. The crew is effectively alone, cut off from the support network that has been proven essential for psychological well-being on long-duration missions aboard the International Space Station, where a video call home is always an option. This forced self-reliance places an enormous burden on the crew's interpersonal dynamics. In such a pressurized environment, a minor annoyance, the way someone eats, a forgotten chore, a difference of opinion, can fester and grow into a major conflict with no easy outlet for resolution. There's no separate room to cool off in, no third party to mediate, and no way to simply take a walk to clear your head. You are trapped with the same few people, and the success of the mission and your survival depends entirely on your ability to get along. Perhaps one of the most disorienting effects is the total warping of time perception. Without the 24-hour cycle of day and night, the body's natural circadian rhythms can become deeply disrupted, leading to sleep disorders, chronic fatigue, and irritability. But beyond the biological clock, the psychological perception of time itself begins to distort. Days can feel agonizingly long, filled with monotony and routine, while simultaneously, months can seem to blur together into one endless, featureless stretch. This temporal confusion can lead to apathy, a decline in motivation, and difficulty concentrating on critical tasks. The mind, desperate for stimulation, can turn inward in negative ways, fueling anxiety about the mission, worries about home, or even the development of irrational fears and paranoia. History's terrestrial analogues, like crews overwintering in Antarctic research stations or individuals in sensory deprivation tanks, have shown that these conditions can lead to vivid hallucinations, severe depression, and acute cognitive impairment. In the context of a space mission where every crew member's performance is vital, a single person's psychological breakdown could jeopardize everything. The emptiness of space, therefore, doesn't just threaten the body, it lays siege to the mind, challenging our very essence as social, sensory beings in a way that no amount of physical training can fully prepare us for. But if the mind can falter in the emptiness, so too can the machines we rely on. And one of the most fundamental challenges of deep space travel is answering a deceptively simple question: where are we? For all of human history, navigation has been an act of looking outward. Ancient mariners charted their course by the sun and the stars, using the fixed patterns of constellations as a celestial map. Pilots flying over featureless oceans still have a horizon line, cloud formations, and eventually radio beacons to guide them. Even in low Earth orbit, astronauts can glance out the window and see the familiar coastlines of continents sliding by beneath them, a constant and comforting confirmation of their position and velocity. But in the deep void between planets, all of these reference points vanish. You are adrift in a sea of absolute black, where the stars themselves become fixed and unmoving pinpricks of light, offering no sense of movement or scale. This complete absence of visual cues creates a navigational nightmare, where a tiny error in calculation or a momentary system glitch could send a spacecraft hurtling silently off into the infinite abyss, never to be heard from again. The technological solution to this problem is a complex web of systems that must work in perfect harmony, each with its own vulnerabilities. The primary method for interplanetary navigation is radio tracking. Giant antennae on Earth, like those in NASA's Deep Space Network, send precise signals to the spacecraft, which then returns them. By measuring the exact time it takes for that signal to make the round trip, engineers can calculate the spacecraft's distance with incredible accuracy. By analyzing the Doppler shift in the signal's frequency, the same effect that makes a siren change pitch as it passes you, they can determine its speed relative to Earth. This system is a marvel of engineering, but it has one colossal weakness. It is entirely dependent on Earth. The farther a spacecraft travels, the longer that communication delay becomes, and the fainter the signal gets. A craft on its way to Mars might be able to rely on this method, but for a mission to the outer solar system or beyond, the signal could take hours to arrive and would be so weak it could be drowned out by the background static of the universe itself. A spacecraft truly on its own in the void would be utterly blind without a way to navigate independently. This is where onboard systems like celestial navigation and inertial guidance come into play, and where the emptiness of space reveals another layer of danger. A spacecraft can carry star trackers, sophisticated cameras that lock onto the patterns of known stars to determine its orientation, much like a sailor using a sextant. But in the vast, uniform blackness between galaxies, even the stars can appear strangely similar. and a computer's misidentification of a single star could lead to a catastrophic error in attitude control. Then there are the inertial measurement units, or IMU. These are hypersensitive devices containing gyroscopes and accelerometers that measure every tiny change in the spacecraft's rotation and movement. They are the ultimate dead reckoning tools. They know how you've moved, but not where you are. The critical flaw is that these instruments suffer from something called drift. Over time, minuscule errors a fraction of a degree per hour accumulate. Uncorrected, these tiny mistakes compound into massive positional errors over the months and years of a long journey. It's like trying to walk in a perfectly straight line across a huge, dark field with your eyes closed. Even if you start perfectly, you will inevitably and unknowingly begin to veer off course. This technological precarity is matched by a deeply human factor, the complete disorientation felt by the crew. Without any external visual confirmation of movement, the human brain loses its ability to gauge speed and direction. Is the spacecraft moving at all? Is it turning? Is it tumbling? This sensory conflict can lead to severe space motion sickness, impairing a crew member's ability to function. But more insidiously, it can breed a dangerous distrust of the instruments. If the screen says you are accelerating but your inner ear insists you are perfectly still, which do you believe? History is filled with tales of pilots in flat spin conditions crashing because they trusted their own flawed sensations over their gauges. In the void of space, that same psychological battle could play out with infinitely higher stakes, potentially leading a crew to manually override a correct computer navigation command, sealing their own fate. The emptiness, therefore, doesn't just remove the road signs. It actively undermines both the machine and the human mind's ability to read the map, turning every journey into a high-wire act where the only safety net is a fragile, error-prone web of technology operating in the most unforgiving environment imaginable. While the silence and isolation of the void prey on the mind, the physical environment presents an equally brutal and paradoxical reality, a desperate struggle against the cold. The popular image of space might be one of fiery stars and sunlit planets, but the overwhelming majority of the cosmos is dominated by a cold so profound it defies earthly comprehension. In the perpetual shadow of deep space, far from the warming embrace of any star, temperatures plummet to within a few degrees of absolute zero, the theoretical point where all molecular motion ceases. This isn't just winter cold, this is a fundamental, active draining of energy, a cold that seeks to still everything it touches. For a spacecraft and its human occupants, this transforms the emptiness from a mere backdrop into an actively hostile force, a freezing trap that demands constant vigilance and immense energy to survive. The challenge of thermal regulation is a constant, high-stakes battle fought on two opposing fronts. A spacecraft must simultaneously find a way to shed the intense heat generated by its own internal systems, computers, electronics, life support, and the crew's own body heat, while also protecting itself from the deep freeze waiting just inches away on the other side of the hull. If it fails to reject enough internal heat, the ship becomes an oven, cooking its inhabitants and frying its sensitive electronics. But if it loses too much heat to the void outside, it becomes a refrigerator, its systems freezing solid and its life-giving fluids turning to ice. This delicate balancing act is made infinitely more complex by the nature of space itself. On Earth, we regulate temperature through conduction and convection. We heat our homes with radiators that warm the air, or we cool our engines with fans that blow air over them. In the vacuum of space, there is no air. There is nothing to conduct heat away or to convect it. The only way for a spacecraft to shed its waste heat is through radiation, a slow and inefficient process that requires large, specialized surfaces to achieve. This is why satellites and space stations are covered in gleaming gold or silver blankets, multi-layer insulation, or MLI. These are not just for show, they are a masterpiece of thermal engineering. Each layer is incredibly thin, often no thicker than a piece of paper, and they are separated by tiny spaces. This creates a series of near vacuums between the layers, drastically slowing the transfer of heat from the warm inside to the cold outside. Meanwhile, the spacecraft must also deploy radiators, panels often attached on long booms, which are painted black to maximize their ability to radiate infrared energy out into space. These radiators are critical lifeblood for the ship, but they are also incredibly vulnerable. A micrometeoroid puncture could leak vital coolant fluid, and even a thin layer of dust from a thruster firing or a foreign object could coat their dark surfaces, reducing their efficiency and potentially leading to a dangerous overheating situation. The extreme cold itself is a direct threat to the very materials that make up the spacecraft. Metals and alloys behave very differently at these cryogenic temperatures. Some become incredibly brittle, losing their flexibility and toughness. A component that could withstand a sharp impact at room temperature might shatter like glass in the deep cold of space. Seals and gaskets made of rubber or other polymers can harden and crack, leading to catastrophic leaks of air or fluid. Lubricants that keep moving parts functioning smoothly can freeze solid, seizing up critical mechanisms like antennae, solar panel joints, or docking hatches. Even the fuel and oxidizer stored in the tanks for engines and thrusters are susceptible. Some propellants must be kept within a very specific temperature range to remain liquid and usable. If they get too cold, they could freeze, and if they get too warm from the ship's internal heat, they could boil away. The spacecraft must constantly use electrical heaters to warm these crucial components, a power drain that never stops from launch until the end of the mission. For the human crew, this thermal war is a matter of life and death on the most immediate level. The spacesuit, that iconic symbol of exploration, is in reality a personal, miniature spacecraft, and it faces the same brutal thermal challenges. During a spacewalk on the sunlit side of a vessel, an astronaut can be roasted by direct solar radiation, with the suit's outer layer reaching temperatures high enough to fry an egg. But the moment they move into the shadow, that same suit is plunged into the deep freeze. The internal cooling and heating systems must work overtime to maintain a safe, stable temperature for the person inside. A failure in this system would be swiftly fatal, either a rapid overheating leading to heat stroke or a chilling drop toward hypothermia. Inside the ship, the climate control system is the silent guardian of crew health, constantly processing the air to remove excess heat and humidity from the crew's breath and sweat, all while ensuring that every surface, every wall, and every window remains warm enough to prevent condensation from forming, which could short out electronics or foster the growth of dangerous mold. In the emptiness of space, there is no comfortable room temperature. There is only the searing heat of the sun and the absolute zero of the shadow, and survival depends on a fragile, energy-intensive bubble of technology, maintaining a precarious and precious island of warmth in an infinite, freezing sea. This terrifying reality brings us to perhaps the most fundamental and chilling vulnerability of deep space travel: the absolute, unbridgeable remoteness. In the emptiness between worlds, a spacecraft is not just a vehicle. It is a single, fragile bubble containing an entire world for its crew. Every hum, every beep, every breath of recycled air is a testament to the flawless functioning of incredibly complex and interdependent systems. But space is the ultimate test of entropy, where everything tends toward disorder, and a single point of failure in this delicate web of machinery can unravel everything. Unlike a voyage across an ocean or even a mission in low Earth orbit, there is no Coast Guard to call, no possibility of an emergency return in a matter of hours, and no rescue ship waiting on standby. A serious problem here means the crew is utterly, completely on their own, facing a countdown clock with no one to hear it tick but them. Consider the most critical system, life support. This is the technological miracle that performs the functions our planet does for free. It scrubs carbon dioxide from the air, carefully balancing the oxygen levels to keep the crew alive but not create a flammable atmosphere. It manages humidity, condensing water vapor from the air and from the crew's breath and sweat, purifying it for drinking and cooling systems. It regulates temperature, fighting the extreme cold and heat outside. A failure in any one of these loops is not a minor inconvenience. It is an immediate and dire emergency. A faulty sensor could allow carbon dioxide to build up to toxic levels, slowly inducing headaches, confusion, and eventually unconsciousness. A pump failure in the water recycling system could lead to a catastrophic flood, shorting out electronics, or worse, it could mean the slow, agonizing loss of the crew's finite water supply. These are not hypotheticals. The Apollo 13 mission famously survived a catastrophic explosion, but their real battle was a life support crisis, a failing system for removing carbon dioxide that forced the crew and ground controllers to ingeniously MacGyver a solution using only the spare parts and materials on board. In the deep void, that kind of ground support would be hours or days away, turning a brilliant save into a tragic footnote. Beyond the air they breathe, the crew's survival depends on the ship's ability to move and communicate. A propulsion failure could strand the spacecraft, turning it into a permanent tomb drifting silently through the void. Without the ability to perform course corrections, a ship bound for Mars could miss its target by millions of miles, shooting past the planet into an endless solar orbit with no hope of recovery. Even more isolating is a communication failure. The complex network of antennas and transceivers is the only tether to Earth, the sole source of guidance, comfort, and assistance. If that link goes silent, the crew is plunged into true isolation, cut off from the immense brainpower of mission control, unable to receive updated navigational data or software patches for unforeseen problems. They become the most alone humans in history, forced to become their own mission controllers, engineers, and doctors with only the knowledge and resources they brought with them. This is why the entire philosophy of spacecraft design for these missions is built upon two pillars: redundancy and reliability. Every critical system has a backup, and often a backup for the backup. Multiple independent computers run in sync, so if one fails, another can instantly take over. Life support systems are duplicated, with valves and pumps that can be rerouted through alternative pathways. Power systems have multiple buses and cross ties, but redundancy adds weight, complexity, and cost, and it can only go so far. You cannot have an infinite number of backups. Furthermore, a single event, like a penetrating micrometeoroid strike or a rampant electrical fire, could cripple primary and backup systems simultaneously. Therefore, reliability is even more crucial than redundancy. Every component, from the largest engine to the smallest microchip, must be designed, tested, and built to a standard of robustness that is almost unimaginable in terrestrial applications. It must withstand violent vibrations during launch, years of exposure to radiation, and the wild temperature swings of space, all without failing. The margin for error is zero. A 10-cent resistor that would be considered disposable on Earth becomes a potential single point of failure that could doom a billion-dollar mission and the lives of everyone on board. In the deep void, there are no small problems, only catastrophic ones, and every piece of technology must be trusted with the ultimate responsibility. Even as the ship's systems work flawlessly to maintain a bubble of life, a different kind of distance begins to impose its own unique form of strain, one measured not in miles but in the agonizing, silent stretch of time between a question and its answer. This is the profound challenge of communication latency, a technical term that barely captures the psychological weight of a conversation where every exchange is a recorded message sent into the void with no hope of an immediate reply. On Earth, even in our most remote outposts, we exist in a state of near instantaneous connection. A distress call brings help, a question to an expert yields an answer, a moment of fear can be soothed by a loved one's voice in real time. In the emptiness of deep space, that fundamental tether of human interaction is stretched to its breaking point, transforming every conversation into a series of monologues and turning the spacecraft into the most isolated library in the universe. The mechanics of this delay are dictated by the unbreakable law of physics. No information can travel faster than the speed of light. While that speed is astonishingly fast on a human scale, it becomes achingly slow across the vast gulfs between planets. A crew on their way to Mars, for instance, will experience a communication delay that grows from a few minutes to a maximum of around 22 minutes each way. This means a simple question like, "What does this instrument reading mean?" takes 44 minutes to receive a response, but consider a mission to the outer solar system, to Jupiter or Saturn. There, the one-way light time can stretch to over an hour. A crisis unfolding aboard the ship would be over and done with long before mission control on Earth even received the first signal that something was wrong. This lag fundamentally rewrites the book on mission operations. The familiar, dynamic chatter between astronauts and mission control, a staple of films and low Earth orbit missions, becomes impossible. There can be no real-time troubleshooting, no collaborative problem-solving, no walking a crew through a complex repair procedure step by step. The crew is, for all practical purposes, entirely on their own. This forces a complete shift in operational philosophy, from a model of remote support to one of ultimate autonomy. The crew must become their own mission control, their own engineering team, and their own medical response unit. They cannot call for help, they must be the help. Every procedure, every contingency plan, every piece of software, and every ounce of their training must be contained within the spacecraft itself. This places an immense burden on the crew's knowledge, composure, and ability to work together under unimaginable pressure. A mistake that might be quickly corrected by a team of experts on the ground could spiral into disaster out here, with no safety net of collective intelligence to catch them. The delay turns decision-making into a lonely and weighty responsibility, where every choice must be made with the sobering knowledge that there will be no second opinion, no confirmation, and no one to share the blame if things go wrong. Beyond the operational nightmare, this communication chasm exacts a heavy toll on the human spirit. The psychological impact of this delayed connection is a form of chronic, low-grade distress. The ability to hear a familiar voice, to share a moment of joy or a concern, is a fundamental human need for emotional regulation. On the International Space Station, astronauts have a scheduled private video conference with their families once a week, a vital lifeline that helps them cope with the stress of separation. In deep space, that lifeline becomes a ghostly echo. A crew member celebrating a birthday cannot share the moment with their family. They can only record a message of their celebration and then wait hours to receive a chorus of "Happy Birthday" that feels disconnected from the event itself. More gravely, during a moment of personal crisis, worrying about a sick child or an aging parent back on Earth, they are completely cut off from the flow of information and comfort. News from home, whether good or bad, arrives not as a live update but as a history lesson, a report on events that have already been concluded, rendering the crew powerless to react or offer support. This forced emotional distance can foster a sense of guilt, helplessness, and profound disconnection, making the Earth they left behind feel not like a home they are connected to, but a distant blue dot they are merely observing from an irreparable remove. The very architecture of communication reinforces this isolation. The famous phrase, "Houston, we have a problem," exemplifies the interactive dialogue of near-Earth missions. In the void, communication becomes a one-way data dump. The crew spends a portion of each day compiling a lengthy report, a digital log of system statuses, scientific data, and personal messages, and fires it like a message in a bottle into the cosmic ocean. Hours later, they receive a similar data packet from Earth, filled with instructions, news, and personal replies. It lacks the spontaneity, the nuance, and the emotional immediacy of a true conversation. There are no interruptions to clarify a point, no tone of voice to interpret in real time, no shared laughter or moment of silent understanding. This sterile, transactional form of interaction can make the crew feel less like explorers in conversation with their species, and more like automatons simply processing data, further deepening the sense that they are utterly alone in the silent, watching dark. Yet for all the very real dangers of radiation, debris, and isolation, the void holds an even deeper and more profound mystery, one that challenges our fundamental understanding of the cosmos itself. We've explored how what we call empty space is filled with sparse atoms and dangerous particles, but these are merely the visible crumbs on a much larger, hidden table. The overwhelming majority of the universe's content is made of substances we cannot see, touch, or directly detect: dark matter and dark energy. These are not just scientific curiosities, they are the dominant forces shaping the cosmos, and their invisible presence in every cubic inch of the void adds a layer of existential risk that is far more subtle, yet potentially more consequential than any physical threat. Let's start with dark matter. We know it exists because we can observe its gravitational effects. Galaxies, including our own Milky Way, rotate at such incredible speeds that the visible matter, all the stars, gas, and dust, should not be enough to hold them together. According to the laws of gravity, these galaxies should have flown apart billions of years ago. The fact that they didn't tells us there must be something else there, providing the extra gravitational glue. This something is dark matter. It is believed to be a kind of particle that does not interact with light or ordinary matter in any way except through gravity. It simply passes through everything, a ghostly sea of particles flowing through the walls of your house, through the earth, and through you right now, utterly unnoticed. In the emptiness of space, this sea is just as present, its gravitational influence subtly tugging on everything it touches. Now consider dark energy, which is an even more bizarre and dominant phenomenon. In the late 1990s, astronomers made a shocking discovery. Not only is the universe expanding, but the rate of that expansion is accelerating. Something is actively working against gravity, pushing galaxies apart from one another at an ever-increasing speed. This repulsive force, this anti-gravity, is what we call dark energy. Current models suggest it makes up about 68% of the entire universe. It isn't a particle, it seems to be a property of space itself. The emptier space becomes as the universe expands, the more dark energy there appears to be, creating a feedback loop of accelerating expansion. So, how do these enigmatic forces add danger to space exploration? The primary risk is not that a clump of dark matter will slam into a spacecraft. That's incredibly unlikely given its diffuse nature. The danger is one of navigation and prediction. Our entire understanding of celestial mechanics, the math we use to plot a course from Earth to Mars or to the moons of Jupiter, is based on a map of the solar system that we now know is incomplete. We calculate trajectories based on the gravitational pull of the Sun and the planets, all visible masses. But what if there are concentrations of dark matter whose gravity we cannot directly see, subtly altering the path of a spacecraft over millions of miles? A tiny, unaccounted-for gravitational tug over the course of a year-long journey could result in a spacecraft missing its target by thousands of miles. While the distribution of dark matter on a large galactic scale is somewhat understood, its behavior on smaller scales, like within our solar system, is still a major unknown. Navigating through the void, therefore, means navigating through an invisible gravitational landscape we have only just begun to chart. The implications of dark energy are even grander and more existential. It dictates the ultimate fate of the entire cosmos. If the acceleration continues unchecked, it points toward a big freeze or heat death, a future where the universe expands so rapidly that galaxies, stars, and eventually matter itself are ripped apart, leaving a cold, dark, and utterly empty void. This is not a danger for our next mission to Mars, but it is a profound danger to our long-term understanding and our place in the universe. It represents a fundamental gap in our knowledge of physics. If we misunderstand the true nature of dark energy, our entire cosmological model, the story we tell about where we came from and where we are going could be catastrophically wrong. For a species aiming to become interplanetary and perhaps one day interstellar, this isn't just academic. It's about understanding the very stage upon which our future will unfold. The emptiness of space is not a passive backdrop. It is actively stretching and evolving due to a force we do not comprehend, and to travel through it is to place our trust in a physics that is, in many ways, still being written. While the gravitational pull of planets and stars can be calculated with incredible precision, the void between them is not the featureless, uniform plane we might imagine. Instead, it is a landscape of invisible hills and valleys, shaped by the subtle and often hidden influence of mass. These gravitational anomalies are regions where the pull of gravity is slightly stronger or weaker than the surrounding area, and they pose a unique navigational hazard precisely because they are so difficult to map and predict. A spacecraft traveling on what appears to be a perfect trajectory can be gently, silently tugged off course by these unseen forces, a deviation that might seem minuscule at first, but that grows into a catastrophic error over the millions of miles of an interplanetary journey. The most common source of these anomalies is the uneven distribution of mass within celestial bodies. We tend to think of planets and moons as perfect, uniform spheres, but they are far from it. They are lumpy, with continents, mountain ranges, and vast deposits of dense minerals all contributing to a gravitational field that is slightly stronger in some places and weaker in others. For a satellite in low orbit, these tiny variations are well studied and mapped. They cause a satellite's orbit to precess or wobble in predictable ways. But for a craft traveling through deep space, the anomalies are caused by the gravitational influence of these entire, distant, lumpy bodies. While the main gravitational pull is from the planet's core, the unevenness adds a complex, whispering layer of perturbation that must be accounted for in flight software. A failure to accurately model these subtle forces could mean the difference between a successful orbital insertion around Mars and a humiliating, mission-ending flyby. Beyond the known lumpiness of planets, there is the far more enigmatic influence of mass concentrations we cannot see. This brings us back to the profound mystery of dark matter. While it doesn't clump together like ordinary matter, its distribution is not perfectly smooth. Theories suggest it could form diffuse streams or low-density clouds within our solar system. Because we cannot see it or directly detect it with our current instruments on board a spacecraft, its gravitational influence is a complete unknown in our navigation equations. A spacecraft could fly through a region of slightly higher dark matter density and experience a tiny, unplanned acceleration that would never be attributed to its true cause. Over time, this could lead to a navigational drift that ground controllers would struggle to explain, potentially writing it off as a minor thruster leak or a measurement error, while the true culprit remains utterly invisible and undetectable. Then there are the theoretical possibilities that, while less likely, highlight the sheer unpredictability of the void. Could there be rogue asteroids composed of unusually dense material, too dark and cold to be seen by our telescopes, lurking in the emptiness? What about the remnants of ancient planetary collisions, fields of dense debris whose collective gravity could create a localized ripple in spacetime? While the probability is low, the consequences of encountering such an unseen obstacle are immense. It wouldn't be a kinetic impact, but a gravitational one. The spacecraft wouldn't crash into it. It would simply find its path curved unexpectedly, pulled toward something it cannot see. By the time the course deviation was noticeable on Earth, it might be too late to correct without a significant expenditure of precious fuel. This navigational challenge forces engineers to adopt a strategy of constant correction and verification. Unlike a car on a highway that can mostly steer itself in a straight line, a spacecraft in the void is constantly making tiny adjustments. It uses its star trackers and gyroscopes to maintain its attitude, and it periodically fires its small reaction control thrusters to nudge itself back onto the precise course calculated by ground controllers. But each of these corrections consumes propellant, the one resource that is absolutely finite and impossible to replenish out there. A journey through a region of unexpected gravitational anomalies would force the spacecraft to burn far more fuel than planned to stay on course, potentially leaving it without enough for the critical braking maneuver needed to orbit its destination, or even worse, for the return trip home. The emptiness of space, therefore, is not a smooth sail. It is a constant, invisible battle against subtle and unseen currents, where victory is measured in ounces of remaining fuel and millimeters per second of velocity change. This relentless dependency on finite supplies transforms every deep space mission into a high-stakes exercise in extreme resource accounting, where the margins for error are razor-thin and the consequences of miscalculation are absolute. Unlike explorers on Earth who might forage for food or find fresh water, a spacecraft venturing into the void is a completely closed system, a tiny island of life sailing on an ocean with no ports, no provisions, and no possibility of resupply. Every single thing needed for survival, every breath of air, every sip of water, every morsel of food, and every drop of fuel for course corrections must be meticulously calculated, packed, and launched from Earth at an astronomical cost. This turns mission planning into a life-or-death equation, a constant battle between the desire to bring enough for safety and the brutal physics of the rocket equation, which dictates that every additional kilogram of mass requires exponentially more fuel to lift it out of Earth's gravity well. The most immediate and critical resources are those that sustain the crew: are oxygen, water, and food. A human being requires about 1 kilogram of oxygen, 3 kilograms of water, and 2 kilograms of food per day just to survive. For a crew of 4 on a 3-year round trip to Mars, that adds up to over 22,000 kilograms of consumables, a mass equivalent to a fully loaded school bus that would be utterly impossible to launch. The only viable solution is to break from the disposable model and create a largely closed-loop life support system, a technological ecosystem that recycles and reuses as much as possible. On the International Space Station, this is already a remarkable reality. Water recovery systems purify and recycle about 90% of the water on board, reclaiming it from humidity in the air, sweat, and even urine. Oxygen is generated by using electricity to split water molecules into hydrogen and oxygen in a process called electrolysis. These systems are engineering marvels, but they are also notoriously finicky and energy-intensive. A major failure in the water recycler on a deep space mission wouldn't just mean an inconvenience, it would start a grim countdown. The crew would be forced to rely on their dwindling emergency reserves, and every drop would be measured and rationed, turning a mission of discovery into a desperate struggle for survival with no hope of a timely rescue. Then there is the propellant, the lifeblood of any voyage. This isn't just about the large engines used for major maneuvers. It's the constant, tiny adjustments made by smaller thrusters to maintain attitude, correct course, and eventually slow down to orbit a destination. In the navigational minefield of the void, with its gravitational anomalies and micrometeoroid avoidance maneuvers, a mission could easily require more propellant than initially planned. Running out of fuel in deep space is a fate worse than running out of air or water. It means the complete and irreversible loss of control. The spacecraft would become a ghost ship, locked into a helpless trajectory, its crew alive but doomed to drift forever on a predetermined path through the endless dark, a monument to a single miscalculation. The tyranny of the rocket equation makes carrying vast extra reserves of fuel completely impractical, so engineers are pioneering new solutions. They are developing more efficient propulsion systems, like ion thrusters that use electrical fields to accelerate ions to tremendous speeds, providing a gentle but continuous push for a fraction of the propellant mass of chemical engines. There is also active research into in situ resource utilization, the concept of mining essentials from the destination itself. For a Mars mission, this could mean manufacturing propellant from the Martian atmosphere, but for a journey through the pure void between planets, there is simply nothing to mine. The emptiness offers no refuge and no resupply. This stark reality is driving innovation in the most fundamental ways. Scientists are exploring the limits of biological recycling, experimenting with growing food hydroponically on board to provide fresh nutrients and help recycle carbon dioxide. But these systems also consume precious power and volume. The management of these resources becomes the central rhythm of daily life for the crew, a constant background hum of monitoring levels, running diagnostics on recyclers, and strictly adhering to consumption protocols. A single extra minute in the shower, a small leak in a water line, or an unplanned thruster firing doesn't just represent a minor technical hiccup. It represents a tangible reduction in the mission's safety margin and a direct threat to its ultimate success. The void, in its absolute scarcity, forces a level of discipline and efficiency that is unparalleled in human experience, making every action, no matter how small, a calculated part of the grand equation of survival. But just as a spacecraft must carefully manage its finite resources, it must also contend with a danger that is not constant and subtle, but sudden and violently explosive: the wrath of our own star. The Sun, the source of all life on Earth, becomes a capricious and deadly adversary in the void. It is not the placid, yellow disk we see from our planet's surface. It is a seething, turbulent ball of plasma. constantly convulsing with eruptions that can unleash hellish storms of radiation across the solar system. These solar flares and coronal mass ejections represent one of the most unpredictable and acute dangers of deep space travel, events that can turn a quiet journey through the emptiness into a frantic race for survival with virtually no warning. A solar flare is a sudden, intense flash of brightness that occurs near the sun's surface, a release of magnetic energy so powerful that it can, in mere minutes, heat solar material to tens of millions of degrees and accelerate electrons, protons, and heavier ions to nearly the speed of light. This creates a massive burst of radiation across the entire electromagnetic spectrum, from radio waves to gamma rays. But the more dangerous event for spacefarers is often the coronal mass ejection, or CME, that can accompany a flare. This is a colossal cloud of billions of tons of solar plasma, threaded with magnetic fields, that is hurled out into space. If this cloud is aimed toward a spacecraft, it becomes a tidal wave of high-energy, charged particles rushing outward at millions of miles per hour. Here on Earth, we are blissfully shielded from the worst of these storms. Our planet's magnetic field acts as a protective bubble, deflecting the charged particles toward the poles where they create the beautiful auroras, while our thick atmosphere absorbs the incoming radiation. A spacecraft in the void has no such protection. It is utterly exposed. The first sign of trouble would be a sensor spike, a frantic alarm as radiation monitors suddenly go off the scale. For the crew, there would be no visible cue, no approaching cloud, no flash of light. The sun would look exactly the same out the window, yet within minutes, the ship would be bathed in a torrent of radiation far more intense than the usual background cosmic rays. The effects on the spacecraft's electronic systems would be immediate and potentially catastrophic. These high-energy particles can slam into a computer's microchips, causing single-event upsets, bit flips that can corrupt data, trigger faulty commands, or even cause a complete system reboot at a critical moment. More severe is the risk of latch-up, where a particle strike creates a short circuit within the chip, permanently damaging it. A major solar storm could effectively fry the delicate electronics that control navigation, life support, and communication, turning a sophisticated vessel into a silent, drifting hulk. The intense radiation can also charge the exterior of the spacecraft, leading to electrostatic discharges, like miniature lightning bolts arcing across the hull that can further damage sensitive external sensors and antennas. For the crew, the biological danger is even more dire. Sheltering inside the ship offers some protection, but the aluminum hull of a typical spacecraft is poor at stopping these high-energy particles. The astronauts would need to retreat to a designated storm shelter, a small area perhaps lined with their water stores or other materials that provide better shielding. Even then, they would receive a significant dose of radiation in a very short time. This acute exposure can cause radiation sickness, with symptoms including severe nausea, vomiting, fatigue, and a drastically reduced count of infection-fighting white blood cells. It dramatically increases their lifetime risk of developing cancer and can cause irreversible damage to the central nervous system and cognitive function. In the most extreme scenarios, an unshielded crew caught in the direct path of a powerful coronal mass ejection could receive a lethal dose in a matter of hours. The most terrifying aspect of these storms is their sheer unpredictability. While we can observe sunspot activity and predict periods of higher probability, we cannot forecast a specific major flare or CME with more than a few tens of minutes of warning. The processes that trigger them deep within the sun's magnetic fields are not fully understood. This means a crew months into a journey to Mars would have, at best, a short heads-up from solar observatories near Earth before the particle wave arrived. Their survival would depend entirely on the robustness of their shielding and the speed with which they could secure themselves and their ship's systems. This constant, low-level anxiety, the knowledge that their star could turn on them at any moment without pity or warning, adds another profound psychological layer to the peril of the void. A reminder that the emptiness is not just cold and dark, but can also be suddenly, violently, and invisibly ablaze. Beyond the violent outbursts of our sun and the silent drift of gravitational fields, the void conceals an even more fundamental and bewildering layer of reality, one that operates on a scale so small it challenges the very definition of what is real. This is the quantum vacuum, and it is anything but empty. According to our most successful laws of physics, what we perceive as a complete void is in fact a seething, bubbling foam of energy, a subatomic frenzy where particles and forces flicker in and out of existence in a constant, chaotic dance. These are quantum fluctuations and virtual particles, and while they might sound like abstract concepts from a physicist's chalkboard, they represent a profound mystery that could have very real implications for the future of technology and travel in the deepest reaches of space. The cornerstone of this bizarre reality is Werner Heisenberg's uncertainty principle, which states in simple terms that we can never know both the exact position and the exact energy of a particle at the same time. This isn't a limitation of our instruments, it's a fundamental property of the universe itself. On the microscopic scale, this uncertainty allows for a remarkable phenomenon: the spontaneous creation of pairs of virtual particles, one particle and its antiparticle, from absolutely nothing. These pairs borrow energy from the vacuum of space itself, existing for an unimaginably short moment before they collide and annihilate each other, paying back the energy loaned so quickly that the universe's books never show a deficit. This isn't a theoretical fantasy. It's a proven effect with observable consequences, such as the Casimir effect, where two metal plates placed extremely close together in a vacuum experience a slight push because the constant creation and destruction of virtual particles outside the plates exerts more pressure than the more restricted activity between them. For the most part, this quantum jitter is just background noise, an interesting footnote to the laws of physics. But when we start talking about the immense scales of energy, distance, and precision required for interstellar travel, these tiny fluctuations could introduce unforeseen and potentially dangerous uncertainties. Imagine an incredibly sensitive navigational instrument, one that relies on measuring minuscule changes in gravity or detecting faint gravitational waves to chart a course. The constant popping in and out of existence of virtual particles would create a faint, omnipresent static at the quantum level, a background hiss that could obscure the very signals the instrument is designed to detect. It would be like trying to hear a whisper in a room filled with the constant, random crackle of static electricity. For a spacecraft relying on such exquisite measurements to navigate the featureless void, this quantum noise could introduce tiny, accumulating errors in its position and trajectory, errors that might not be discovered until it was far too late to correct them. The risks become even more speculative but far more dramatic when we consider the theoretical extremes of engineering. Some far future concepts for interstellar travel, like the Alcubierre warp drive idea, involve manipulating the fabric of spacetime itself to create a bubble that moves faster than light. Such a concept would require generating and controlling immense amounts of negative energy or exotic matter, conditions that would intensely interact with the quantum vacuum. The concern among some theoretical physicists is that the boundary of such a warp bubble could become unstable due to these quantum fluctuations. The seething quantum foam could potentially amplify into a catastrophic energy burst at the leading edge of the bubble, unleashing a shower of high-energy particles that would vaporize anything at the destination point the moment the ship dropped out of warp. In this scenario, the very mechanism that allows for faster-than-light travel would also make it a weapon of planetary destruction, turning an arrival into an impact event. Even without such science fiction concepts, the quantum vacuum presents a more immediate, though subtle, challenge to the materials and electronics of today's spacecraft. The unpredictable nature of quantum events can contribute to the random soft errors that occasionally flip a bit in a computer's memory, a problem that already plagues satellites and is mitigated through robust error-correcting codes. In the deeper void, over longer missions and with more complex and sensitive systems, this background of quantum uncertainty could become a more significant factor in system reliability, another invisible variable that engineers must account for in their already Herculean task of designing for perfection. The void, therefore, is not just an empty stage for our journeys. It is an active participant, its most fundamental nature whispering with a potential for chaos that reminds us that even in nothingness, the universe is alive with mysterious and untamed energy. History provides us with the most sobering and instructive proofs of the void's dangers, not through theory, but through harrowing real-world events where human ingenuity was pitted against the unforgiving reality of deep space. The most iconic of these is the Apollo 13 mission, a story not of lunar landing, but of survival against impossible odds. When an oxygen tank exploded 200,000 miles from Earth, the crew was suddenly stranded in a crippled spacecraft, their command module dying and their lunar module, never designed for such a role, transformed into a makeshift lifeboat. The emptiness surrounding them was the central antagonist of the drama. It meant there was no abort option that would bring them home quickly. Their trajectory had flung them around the moon, and the return journey would take 4 agonizing days. It meant that every resource, power, water, oxygen, was devastatingly finite. The most famous crisis, the rising carbon dioxide levels that threatened to poison the crew, was a direct result of this isolation. The Square Command Module lithium hydroxide canisters were incompatible with the round openings in the lunar module system. With no hardware store to visit, the ground team on Earth had to invent a solution using only the random items known to be on the spacecraft: plastic bags, cardboard, tape, and a sock. They devised an adapter and read the instructions up to the crew, who built it and lived. Apollo 13 is the ultimate lesson in real-time improvisation, proving that in the void, a crisis cannot be solved by throwing more parts at it. It is solved by the depth of human creativity and the ability to use absolutely everything you have. The International Space Station, though in the relative safety of low Earth orbit, has also had its share of close calls that foreshadow the dangers of deeper space. In 2019, a subtle but terrifying leak was discovered. A tiny hole, likely caused by a micrometeoroid strike or a manufacturing defect, was bleeding air from the Russian Zvezda module. In the depths of the void, such a leak would be a countdown to catastrophe. On the ISS, the proximity to Earth allowed for a methodical, pressurized response. The crew located the leak by using a tea leaf, releasing it into the air and watching its float pattern to find the tiny draft, and sealed it temporarily with tape and epoxy. This incident underscores 2 critical truths. First, the ever-present threat of penetration, even from an object too small to track, is a constant reality. Second, it highlights the irreplaceable value of having a large, complex station with multiple modules. It provided the volume of air that gave the crew time to find and fix the problem. On a smaller spacecraft bound for Mars, that same leak might have depressurized the entire vehicle before anyone could react. A grim reminder that the smaller the island of life, the more vulnerable it is to a single breach. More recently, the experience of the Boeing Starliner spacecraft during its uncrewed orbital flight test in 2019 offers a modern cautionary tale about software and autonomy in the void. A timer error on the spacecraft caused it to burn its thrusters at the wrong time, putting it into the wrong orbit and preventing it from docking with the ISS. Crucially, a second software issue was discovered and fixed during the mission that could have led to a catastrophic failure during re-entry. This incident didn't happen in the deep void, but it powerfully illustrates a danger that would be magnified there: the critical nature of flawless software. A similar glitch on a mission to Mars with a communication delay of 20 minutes could not be corrected by ground controllers in time. The crew would have to rely on their own understanding of the spacecraft systems and their ability to upload patches or command overrides independently. It proves that in the emptiness where real-time help is impossible, the software must be perfect, and the crew must be transformed from operators into master engineers capable of debugging their own life support system while hurtling through space. These historical moments, from Apollo 13's jury-rigged filter to Starliner's software scare, all point to the same indispensable requirement for venturing into the void: resilience. This is not just redundancy, which is having a backup system. Resilience is the capacity to absorb a shock, adapt to the new reality, and continue the mission. It is the combination of robust design, extensive training, and a culture of problem-solving that empowers crews to face the unexpected. The void does not forgive single points of failure. It ruthlessly exploits any weakness, any assumption, any overlooked variable. The lessons learned from these emergencies are now baked into every aspect of spaceflight planning, driving the development of more autonomous systems, more rigorous testing, and cross-training for astronauts so that a pilot can perform medical procedures and a scientist can understand the intricacies of the guidance computer. The history of space exploration is in many ways a history of narrowly avoided disasters, each one teaching us to respect the infinite creativity of the universe in finding new ways to challenge us, and affirming the boundless ingenuity of the human spirit in its relentless drive to overcome them. Faced with these daunting historical lessons and the unforgiving nature of the void, the path forward may lie not in making humans tougher, but in creating partners that are inherently suited to the environment. This is where robotics and artificial intelligence step onto the stage, not as replacements for human explorers, but as indispensable allies designed to shoulder the risks that are simply too great for flesh and blood. These autonomous systems represent a fundamental shift in our approach to deep space, moving from a model of direct human control to one of sophisticated partnership, where machines act as our eyes, hands, and even decision-makers in the most perilous moments. The first and most critical role for these systems is as advanced scouts and sentinels, tasked with perceiving threats that are invisible to human senses. Imagine an AI-powered sensor suite constantly scanning the surrounding void, not just for the large debris we can track from Earth, but for the microscopic dust grains and tiny particles that travel at hypervelocity. Using advanced LiDAR and radar systems, coupled with machine learning algorithms trained on countless simulations, such a system could predict the probability of impact from a cloud of micrometeoroids minutes or even hours before a human operator would ever notice a blip on a screen. This isn't just about sounding an alarm, it's about proactive defense. An integrated AI could automatically calculate and execute a tiny, fuel-efficient thruster burn to adjust the ship's attitude, presenting a more shielded section of the hull to the incoming particles. Or it could even deploy a temporary sacrificial barrier, a concept known as a dust shield, that would absorb the impact and vaporize the threat before it ever reached the main habitation module. When a system does fail or require maintenance, the solution cannot be a spacewalk. The delays in communication make real-time guidance from Earth impossible, and the sheer danger of sending a person outside the ship in the depths of space, surrounded by radiation and debris, is unacceptably high. This is the domain of robotic repair crews. We are already developing dexterous robotic arms and humanoid robots like NASA Valkyrie that can be deployed from an airlock to perform complex external surgery on a spacecraft. Guided by a combination of pre-programmed instructions and autonomous decision-making, these robots could locate a damaged solar panel, diagnose a faulty antenna, or patch a microfracture in the hull. They would be equipped with a suite of tools and, most importantly, the AI brain to use them effectively. If a task takes an unexpected turn, the robot wouldn't need to wait 40 minutes for instructions from Houston. Its onboard neural networks would analyze the new scenario, compare it to its vast training database, and devise a new solution in real time, all while the astronaut crew supervises safely from within, ready to intervene only if the situation exceeds the machine's capabilities. Perhaps the most profound application of AI lies in managing the ship's internal ecosystem, the incredibly complex closed-loop life support system. Keeping humans alive is a dynamic, constant balancing act of oxygen levels, carbon dioxide scrubbing, water purification, and waste management. A glitch in one subsystem can cascade into a crisis in another. An artificial intelligence acting as a master systems engineer could monitor every sensor, every pump, and every valve in real time. It could predict a filter is nearing the end of its life based on subtle changes in flow rate and pressure long before it clogs, alerting the crew to replace it during a scheduled maintenance window rather than in the middle of an emergency. It could continuously optimize power consumption, balancing the needs of the life support against the navigation computers and scientific experiments to ensure the ship always operates at peak efficiency. In a medical crisis, an AI diagnostic tool could analyze a crew member's vital signs, cross-reference symptoms with a vast medical library, and assist the crew medical officer in formulating a treatment plan, potentially even guiding them through a complex procedure using augmented reality displays. This transforms the spacecraft from a machine that must be constantly operated into a living, breathing entity that can largely care for itself and its inhabitants, allowing the human crew to focus on the mission of exploration rather than the full-time job of survival. In the immense and silent void where human error can be catastrophic, the steady, unblinking vigilance of artificial intelligence may become our greatest safeguard. This question of sending humans into such a perilous environment forces us to confront a profound ethical dilemma, one that pits our boundless curiosity and drive for exploration against our most fundamental duty to protect human life. It's a modern version of an ancient conflict, but played out on a stage where the risks are literally astronomical and the safety nets are non-existent. We must ask ourselves not just can we do it, but should we? The answer is not a simple yes or no, but a complex tapestry woven from threads of consent, societal benefit, and the very definition of progress. At the heart of the issue lies the concept of informed consent. The astronauts who volunteer for these missions are among the most highly trained, intelligent, and aware individuals on the planet. They understand the risks in a way few others can, having studied the engineering challenges, the biological hazards, and the historical precedents of things going wrong. They are not naive daredevils, they are calculated risk-takers who have devoted their lives to this pursuit. In this sense, we can argue that their consent is as informed as it is possible to be. However, can anyone truly consent to the unknown? We can brief them on the predicted effects of years of cosmic radiation, but the long-term neurological and cellular damage might hold surprises that our best science has not yet uncovered. We can train them for isolation, but can we truly prepare them for the profound psychological disconnection of being truly alone, with a 20-minute delay on every comforting word from home? There is a difference between understanding a risk on paper and living with its potentially devastating reality, and this gap is where the ethical waters become murky. Beyond the individual, we must consider the societal responsibility. These missions are funded by public money, by taxpayers who entrust their governments and space agencies to act responsibly. If a mission ends in tragedy, the collective grief and trauma would be immense, potentially halting space exploration for a generation, as the Challenger and Columbia disasters did for the shuttle program. The ethical question then expands: does society have the right to spend vast sums on these incredibly high-risk endeavors when that same money could address pressing problems on Earth: poverty, disease, climate change? Proponents would argue that the technological and medical spin-offs from space exploration have historically provided immense benefits to everyone on Earth, leading to advancements in medical imaging, water purification, and materials science. They see it as a long-term investment in human knowledge and survival, a necessary step toward becoming a multi-planetary species and ensuring our existence against a planetary catastrophe. The ethical scales, then, must balance the immediate, certain needs of people today against the potential, uncertain benefits for all of humanity tomorrow. This leads to the final and perhaps most poignant ethical layer: the duty of care owed by the organizations sending people into the void. It is not enough to simply accept the risks. There is a moral imperative to mitigate them to the absolute maximum extent possible. This means prioritizing safety over schedules, investing in redundant systems even when they are expensive and heavy, and fostering a culture where any engineer or technician can voice a concern without fear of reprisal. The ethical mission doesn't end at launch. It extends to the lifelong healthcare and support for the astronauts upon their return, who may face medical issues directly caused by their service. Are we prepared to provide for them if they develop a rare cancer 10 years after their mission? Are we committed to supporting their mental health after the unimaginable experience of deep space travel? The ethics of sending humans into the void are not just about the moment of liftoff, but about the lifelong covenant we make with those brave enough to journey into the darkness on our behalf. Given the monumental challenges of the void, our only path forward is to innovate our way to safety, developing technologies that seem ripped from the pages of science fiction but are steadily becoming scientific fact. The key to surviving the emptiness isn't just to build a stronger hull, but to fundamentally rethink our entire approach to the journey, creating systems that are as dynamic and resilient as the environment they must endure. One of the most urgent puzzles to solve is the ever-present threat of cosmic radiation. The traditional solution of simply adding more metal armor is a dead end. The weight would be prohibitive, and the secondary radiation created when particles slam into a thick metal hull might be as dangerous as the original threat. Instead, scientists are pioneering a new generation of smart shielding. This includes lightweight, hydrogen-rich composites materials like polyethylene or other polymers that are exceptionally good at absorbing and dispersing the energy of incoming particles without creating dangerous secondary showers. Even more promising is the concept of active shielding, which sounds like something from a starship's engineering deck. The idea is to create a miniature magnetic field around the spacecraft, a replica of Earth's protective magnetosphere. By using superconducting coils to generate a powerful magnetic bubble, This system would deflect charged radiation particles away from the ship long before they reach the hull. While the energy requirements for such a system are currently enormous, advances in superconductivity and power generation could one day make this the most effective way to create a safe, radiation-free zone for crews on long-duration missions, turning their vessel into a moving fortress guarded by an invisible force field. To further reduce the crew's exposure, we might also change their fundamental state of being during the most dangerous parts of the journey. This is where the concept of torpor, or induced hibernation, moves from movie fantasy to serious NASA-funded research. The idea isn't to freeze astronauts solid, but to lower their core body temperature and metabolic rate significantly, placing them in a deep, sleep-like state for weeks or months at a time. In this dormant condition, their bodies would require far less food, water, and oxygen, drastically reducing the mass of consumables needed for the trip. More importantly, a hibernating crew would be far less vulnerable to the effects of radiation and the psychological toll of monotony and isolation. Their quarters could be transformed into a heavily shielded central core of the ship, a kind of storm cellar for the entire journey, while the ship itself is run by a sophisticated AI. This AI would not just be a passive monitor, it would be the sole pilot, engineer, and doctor for the duration of the transit, handling navigation, system maintenance, and even running medical diagnostics on the sleeping crew, only waking them if a problem exceeded its capabilities or as the ship approached its destination. This approach doesn't just mitigate risk, it reimagines the human role in spaceflight from active operators to precious cargo, protected and preserved until they are most needed. Of course, the ultimate solution to almost every danger of the void is to simply spend less time in it. This is the promise of advanced propulsion. Chemical rockets, which have taken us to the moon and beyond, are simply not up to the task of swift interplanetary travel. They are too slow and too thirsty. The future lies in systems that offer a constant, efficient push. Ion thrusters, which are already used on many satellites and probes, work by electrically charging atoms of a gas like xenon and accelerating them out of a nozzle using a magnetic field. This creates a thrust that is incredibly gentle but can be maintained for months or even years, allowing a spacecraft to build up tremendous speeds while using a fraction of the propellant of a chemical rocket. For truly revolutionary travel, concepts like nuclear thermal propulsion are back on the table. By using a compact nuclear reactor to superheat a propellant like liquid hydrogen, these engines could provide thrust many times greater than chemical systems, potentially cutting the travel time to Mars in half. Slashing the duration of the voyage directly reduces the crew's exposure to radiation, microgravity, and psychological stress, making every hazard more manageable. These aren't mere incremental improvements. They are paradigm shifts that transform a perilous, years-long expedition into a more manageable months-long commute, bringing the solar system within our practical reach and ensuring that when we send humans into the emptiness, we can do so with the confidence that they won't be trapped there any longer than absolutely necessary. While the spacecraft itself can be armored against radiation and equipped with redundant systems, the human mind presents a vulnerability that cannot be solved by engineering alone. This is why astronauts selected for the most ambitious deep space missions undergo a psychological conditioning process as rigorous and detailed as their physical and technical training. This isn't about simply finding the right stuff. It's about systematically forging mental resilience, equipping crews with a cognitive toolkit to withstand an environment of profound isolation and unremitting stress for which our evolutionary history has left us utterly unprepared. The foundation of this training is built upon extreme analog environments here on Earth, carefully designed to simulate the sensory and social deprivation of the void. Candidates might spend months submerged in a naval habitat on the seafloor, where the world outside is a dark, watery abyss, and their only company is their small crew in a cramped metallic tube. Others are sent to remote Antarctic research stations during the long polar winter, where the sun vanishes for months, temperatures plummet to lethal extremes, and the outside world is completely inaccessible, creating a perfect mirror of the isolation and confinement of a deep space mission. In these controlled yet authentic pressure cookers, trainers observe how individuals and teams handle conflict, manage boredom, and maintain performance when cut off from all normal support systems. They are deliberately presented with simulated emergencies, a sudden drop in cabin pressure, a critical system failure, to see how they problem solve under duress and whether their group cohesion holds or fractures under the strain. Beyond these large-scale simulations, astronauts engage in intense cognitive and behavioral training. They practice advanced communication techniques designed to prevent the minor irritations of close quarters living from escalating into mission-threatening conflicts. This includes learning to express concerns without assigning blame, to actively solicit opinions from quieter crew members, and to de-escalate tensions through structured dialogue. They are schooled in mindfulness and meditation practices, not as a spiritual exercise, but as a practical tool to regulate their own stress responses, manage anxiety, and maintain focus during monotonous tasks. Perhaps most crucially, they are taught to recognize the early warning signs of cognitive decline in themselves and their crewmates' increased irritability, social withdrawal, lapses in concentration, and are given protocols to intervene, offering support or suggesting countermeasures before a small issue becomes a crisis. A significant part of their preparation also involves what might be called existential acclimatization. Through virtual reality, they are exposed to the reality of their future view, the Earth as a distant, fading blue dot becoming smaller and less distinct with each passing day. Psychologists work with them to process the potential feelings of insignificance, disconnection, and homesickness this sight can evoke, helping them reframe it not as a symbol of loneliness but as a beacon of everything they are working to protect and understand. They undergo extensive cross-training, ensuring that each member has a deep understanding of their colleagues' roles. This does more than just provide operational redundancy. It creates a profound sense of interdependent competence, building trust that every person on board is a capable problem solver, which is the ultimate antidote to the helplessness that can fester in a remote and dangerous environment. This meticulous mental fortification ensures that when the hatch closes and the Earth falls away, the crew carries with them an internalized strength, a psychological life support system as vital as any machine that will keep them breathing. But these staggering costs are not just numbers on a spreadsheet. They represent a fundamental constraint that directly shapes every single aspect of mission design, often forcing a brutal calculus between ambition and safety. The primary driver of these astronomical expenses is the tyranny of the rocket equation, which dictates that launching anything into space requires an exponential amount of fuel. Every single kilogram of mass, whether it's a critical piece of scientific equipment, a liter of drinking water, or a sheet of radiation shielding, must be hurled out of Earth's deep gravity well at tremendous cost. This creates an environment where engineers are forced to make agonizing trade-offs. Do we add an extra layer of shielding to protect the crew from a potential solar storm, adding several $1 million to the launch cost and potentially requiring a larger, more expensive rocket? Or do we accept that risk to stay within budget, betting that a warning system and a designated storm shelter will be sufficient? This constant balancing act between mass, safety, and cost means that every mission into the void is, by necessity, an exercise in managed risk. There is no such thing as a perfectly safe spacecraft. There is only a spacecraft that is as safe as the budget allows it to be. These financial pressures ripple through the entire timeline of a mission, from its initial conception to its final moments. The development phase is where costs can spiral most dramatically. Building a spacecraft that can operate autonomously for years in the harshest environment known to humanity requires components that are not just high quality but space-grade. This means every computer chip, every wire, every bolt must be rigorously tested to withstand extreme temperatures, intense radiation, and the violent vibrations of launch. A standard commercial microprocessor that costs $50 on Earth might need to be replaced with a radiation-hardened version that costs $50,000. This pursuit of near-perfect reliability is phenomenally expensive but non-negotiable. A single faulty 10-cent capacitor can doom a multi-billion-dollar mission. Furthermore, the need for redundancy backup systems for every critical function effectively doubles or triples the cost of those systems. A mission might require 3 separate flight computers, each running in sync, so that if one fails, another can instantly take over. This is a direct financial response to the utter remoteness of the void. Since a repair crew cannot be sent, the ability to repair itself must be built in from the start at a premium price. The high risk of total mission failure adds another complex financial layer: insurance. Insuring a satellite bound for geostationary orbit is a well-established industry, but ensuring a crewed mission into deep space is a whole different proposition. The potential loss is so colossal and the unknowns are so vast that traditional insurers are extremely hesitant. This often means that the financial risk is borne by the government agencies funding the missions, effectively making the taxpayer the ultimate insurer. A single catastrophic failure could not only cost lives but could also trigger a political and financial crisis that ends entire exploration programs for decades, as seen after the space shuttle disasters. This ever-present specter of failure forces a deeply conservative approach to engineering. New, revolutionary technologies that could make space travel safer or cheaper are often viewed with skepticism because they are unproven. The adage, "no one ever got fired for choosing the established, reliable technology," is deeply ingrained in spaceflight, and it can stifle innovation. The need to guarantee a return on such a massive public investment inherently favors incremental, tested improvements over bold, revolutionary leaps, potentially slowing our progress into the cosmos precisely because the price of admission is so unbelievably high. This reality that the void is too vast, too dangerous, and too expensive for any one country to conquer alone has fundamentally reshaped the very philosophy of space exploration. The iconic image of a single nation's flag planted on a distant world is being replaced by a more collaborative and ultimately more resilient vision, a global endeavor where the burdens, the costs, and the triumphs are shared. International partnerships are no longer a matter of political preference. They have become an absolute strategic necessity for venturing beyond the safety of Earth's orbit. This shift recognizes that the challenges of the void do not recognize national borders, and our response must be equally unified to stand any chance of success. The most profound benefit of this global approach is the sheer pooling of resources, both financial and intellectual. The development of a spacecraft capable of sustaining human life for a multi-year journey to Mars carries a price tag that could easily cripple the economy of even the wealthiest nation if attempted alone. By distributing these costs across multiple international partners, the financial burden on any single taxpayer base becomes manageable. But more than just money, this collaboration pools the world's brainpower. Each nation brings its own unique strengths and specializations to the table. One country might contribute a revolutionary life support system, the result of decades of research, while another provides an advanced propulsion module, and a third offers cutting-edge radiation shielding materials. This creates a whole that is far greater than the sum of its parts, a spacecraft that is more capable, more redundant, and ultimately safer than anything a single nation could produce on its own. It leverages a global portfolio of technological excellence, ensuring that the final vehicle represents the absolute pinnacle of human engineering from around the world. This shared risk model also extends to the terrifying possibility of failure. A catastrophic accident in deep space would be a human tragedy of unimaginable scale, but if borne by a single nation, it could also be a national trauma that ends that country's space program for a generation. When the risk is shared internationally, however, the responsibility for safety becomes a collective imperative, and the impact of a disaster, while no less tragic, is diffused across a global partnership. This shared accountability fosters an unparalleled culture of transparency and rigorous oversight. Engineers from different countries and agencies scrutinize each other's work, questioning assumptions and challenging designs from diverse cultural and engineering perspectives. This process, while sometimes complex, acts as a powerful safeguard against groupthink and complacency, catching errors that might be missed within a single, insular organization. The International Space Station stands as the ultimate testament to this principle. It is not an American station or a Russian station. It is a truly international outpost, and its uninterrupted operation for over 2 decades is a direct result of this deep, intertwined partnership where every module, every system, and every crew member relies on the contributions of all the others. Beyond the hardware and the finances, international collaboration builds a crucial framework of diplomatic stability for long-term exploration. Space has historically been a realm of competition, but ventures into the void require commitments that span decades, far longer than the typical cycles of geopolitical tensions between nations. By binding countries together in a shared, monumental, and peaceful scientific endeavor, these partnerships create a powerful incentive to maintain dialogue and cooperation, even when relations on Earth become strained. The enduring cooperation between NASA and Roscosmos throughout various earthly political challenges demonstrates how a shared dependency on a space station can foster a level of pragmatic cooperation that benefits all of humanity. This model provides a stable, predictable foundation for planning the next great leaps into the cosmos, ensuring that a change in political winds on Earth does not derail a mission that is years into its journey to another world. In this way, international collaboration does more than just enable us to reach the stars. It helps us build a more cooperative future here on Earth, proving that our greatest explorations are achieved not through competition, but through unity. While the known dangers of the void are formidable enough, the realm of theoretical physics invites us to consider perils that are far more exotic, born from the most extreme predictions of Einstein's theory of general relativity. These are not just hazards in space, but hazards of spacetime itself, cosmic pitfalls that could rewrite the rules of reality for anything unfortunate enough to stumble upon them. The most chilling of these theoretical threats is the concept of a rogue black hole, an invisible predator drifting silently through the interstellar darkness. Most black holes we know of are anchored within galaxies, often at the center or in binary star systems where their presence is betrayed by the violent death dance of the matter they consume. But a rogue black hole is a different kind of monster altogether. it is a solitary wanderer, a relic from the early universe perhaps, ejected from its birthplace by a violent gravitational interaction during a galactic collision. This would leave it completely dark, emitting no light, and with no companion stars whose distortion might reveal its presence. Its only signature would be its immense gravitational field, a subtle warping of the void that would be virtually undetectable until a spacecraft was already perilously close. The danger of such an encounter is not necessarily being pulled in. A black hole's event horizon is relatively small. The true peril lies in the extreme tidal forces that would seize a spacecraft long before it reached that point of no return. As the ship approached, the difference in gravitational pull between the side of the ship facing the black hole and the side facing away would become astronomical. This would stretch the spacecraft and everything in it like taffy, a process physicists gruesomely term spaghettification. The hull would be torn apart, the crew would be subjected to unimaginable forces, and every molecule of the vessel would be shredded into a stream of particles spiraling into the oblivion of the singularity. The most terrifying aspect is the stealth of the attack. There would be no warning flash, no roaring sound. One moment the ship is on course, the next its navigation systems might show an inexplicable and rapidly increasing acceleration towards nothing at all. By the time the crew could even begin to understand what was happening, the tidal forces would already be ripping their world apart, a silent and instantaneous end in the perfect blackness. Equally speculative but no less fascinating is the theoretical danger posed by wormholes, often portrayed in fiction as convenient shortcuts across the galaxy. In theory, a wormhole is a tunnel through the fabric of space-time, a bridge connecting two distant points that could make interstellar travel instantaneous. The mathematics of general relativity allows for such structures, but they are predicated on the existence of a hypothetical form of matter or energy called exotic matter, which possesses negative energy density and negative pressure. This exotic matter would be needed to prop the wormhole's throat open, preventing it from collapsing the instant it formed. The danger here is not just that a wormhole might be unstable, but that its very nature is fundamentally unknown. If one were to be encountered, attempting to traverse it could be the last decision a crew ever made. The interior could be riddled with unforgiving tidal forces, similar to those of a black hole. The exotic matter needed to stabilize it could have bizarre and lethal effects on normal matter, potentially dissolving or transmuting anything that came into contact with it. Perhaps the most unsettling possibility is that the other end of the wormhole might not be where or when you expect it to be. The exit could open in the heart of a star, in the distant past, or in a completely different universe with physical laws incompatible with our own. The journey through could be a one-way trip to an existence of certain and immediate destruction, or a form of eternal exile far more absolute than simply being lost in space. While the chances of randomly encountering a stable, traversable wormhole are infinitesimally small, their theoretical existence serves as a profound reminder that the void may hold complexities we are only beginning to mathematically imagine. These concepts push at the very edges of our understanding, suggesting that the greatest dangers in the cosmos may not be the things we can see and measure, but the hidden fractures and folds in reality itself, lying in wait within the infinite and uncharted dark. This profound disconnection from the world we evolved in reaches into the very fabric of our consciousness, warping our perception of one of the most fundamental aspects of reality, time itself. Our internal clock is not a perfect, isolated mechanism. It is a complex neurological system that relies on a constant stream of external cues to stay synchronized. On Earth, we are surrounded by these timekeepers, the daily cycle of sunrise and sunset, the changing angle of light through a window, the rhythmic patterns of mealtimes and social interactions, even the predictable ebb and flow of traffic outside. All of these environmental signals act as a metronome for our brain, calibrating our internal sense of seconds, minutes, and hours. But in the deep void, this metronome vanishes. The sun is either a constant, unwavering point of light or completely absent, replaced by an eternal star-studded blackness that never changes. There is no dawn, no dusk, no changing seasons, and no external social rhythms beyond the artificial schedule imposed by the mission plan. The spacecraft becomes a timeless capsule, and the human mind inside is left to drift in a sea of its own making, without any anchors to the passing of time. The psychological consequences of this temporal disorientation are both subtle and severe. Without external validation, the brain's internal clock, or circadian rhythm, begins to drift. Studies on Earth, such as those in isolation chambers or with individuals living in caves, have shown that our natural circadian cycle is actually slightly longer than 24 hours. When deprived of sunlight, most people's internal day will naturally shift toward a 25 or even 26-hour cycle. In space, this means an astronaut might feel wide awake when their schedule calls for sleep, or struggle with crushing fatigue in the middle of their work period. To combat this, missions adhere to a strict 24-hour schedule of artificial lighting that mimics a day-night cycle, but it is a poor substitute for the real thing. The body's production of melatonin, the hormone that regulates sleep, becomes disrupted, leading to poor sleep quality, chronic fatigue, and irritability. This sleep deprivation directly impairs cognitive function, slowing reaction times, clouding judgment, and making it harder to concentrate on complex tasks. A dangerous combination when you are millions of miles from help and operating a vessel that demands constant vigilance. Beyond the biological clock, the psychological perception of time undergoes a bizarre transformation. In an environment devoid of new stimuli, where every day is meticulously planned and looks exactly like the last, time can seem to both crawl and fly by in a confusing paradox. The minutes and hours spent on repetitive maintenance tasks or staring at unchanged instrument panels can feel agonizingly slow, a sensation of being stuck in a moment that never ends. Yet when looking back, weeks and months can blur into an indistinguishable mass, with no unique events or changing scenery to act as mental bookmarks. This phenomenon, known as time compression, makes it feel as if the mission has simultaneously lasted forever and yet passed in the blink of an eye. This distortion isn't just a curious mental trick. It can lead to a dangerous sense of apathy and a decline in motivation. If time has lost all meaning and one day is exactly like the next, the urgency of tasks can fade. A crew member might procrastinate on a minor system check or become less meticulous in their data logging, not out of laziness, but because their warped sense of time has disconnected the present action from any future consequence. This erosion of temporal awareness directly threatens the quality of decision-making. High-stakes decisions often rely on an accurate sense of timing and an understanding of how long ago an event occurred or how long a process has been running. In the void, a commander might misjudge how much time has passed since a critical engine burn, leading to a course correction that is too early or too late. A medical officer might inaccurately track the progression of a crewmate's symptoms because their own sense of time's passage is distorted. The problem is compounded by the communication delay with Earth. When every conversation is a series of time-shifted monologues, the very process of collaborative decision-making becomes fractured across a temporal gap, making it difficult to establish a shared, accurate timeline of events. The emptiness of space, by stripping away the cues that ground us in the flow of time, doesn't just make us feel disoriented. It actively undermines the neurological and psychological foundations we rely on to make smart, timely, and potentially life-saving choices in an environment where every second truly counts. While we often picture solar flares as the primary threat from our sun, they are merely the most dramatic symptom of a much broader and more complex phenomenon known as space weather. This is a constant, dynamic state of the space environment, driven by the sun's volatile activity and permeating every corner of our solar system. It encompasses a flowing river of charged particles called the solar wind, shifting interplanetary magnetic fields and vast regions of energized particles trapped in planetary magnetospheres. In the emptiness between worlds, these invisible forces become the prevailing climate, a silent storm that can buffet a spacecraft, confuse its instruments, and sever its connection to home, adding yet another layer of peril to an already treacherous journey. The solar wind is the foundational element of this cosmic climate, a continuous supersonic flow of plasma, mostly electrons and protons, that streams outward from the sun in all directions at speeds averaging 1,000,000 miles per hour. This isn't a gentle breeze, it's a hurricane of charged particles that carries with it the sun's magnetic field, stretching it out through the solar system to form the interplanetary magnetic field. For a spacecraft, this constant flow has a tangible effect. It exerts a slight but persistent pressure on the vessel's surfaces, much like wind pushing on a sail. Over the immense distance of an interplanetary voyage, this pressure must be factored into navigation calculations. An unanticipated gust in the solar wind, a high-speed stream flowing from a coronal hole on the sun's surface, could act like a current in the ocean, slowly pushing the spacecraft off its intended course. This requires mission controllers to periodically fire the thrusters to correct for this drift, consuming precious propellant that cannot be replaced. It's a silent, invisible force constantly at work, trying to steal the ship from its path. These gusts of solar wind also carry with them profound disruptions in the form of co-rotating interaction regions. These are not singular explosive events like flares, but vast, rolling waves of compressed plasma that form when a fast-moving stream of solar wind overtakes a slower-moving one ahead of it. Imagine traffic on a highway suddenly bunching up where a fast lane merges into a slow one. This collision creates a shock wave that accelerates particles and amplifies magnetic fields. For a spacecraft, traversing such a region is like sailing from calm seas into a churning squall. The intensified magnetic fields can induce powerful electrical currents in the ship's structure. These currents can flow into sensitive electronics, causing unexpected glitches, reboots, or even permanent damage to components not hardened against such surges. The crew might notice flickering lights or strange readings on their consoles, the only visible signs of an invisible tempest raging just outside their hull. The most dangerous interactions occur when these solar wind disturbances encounter a planet's magnetic field. However, in the deep void, far from the protective bubble of Earth or any other planet, a spacecraft is directly exposed to these particles. Many of them become energized to extremely high levels, creating vast regions of radiation that ebb and flow with the sun's activity. These populations of energetic particles can quickly surround a spacecraft, creating a hazardous environment that forces the crew to retreat to their storm shelter and postpone any planned spacewalks. The constant bombardment can also degrade external materials over time, darkening camera lenses, damaging solar cell efficiency, and slowly breaking down the insulation on wiring, potentially leading to short circuits months or years into a mission. Perhaps the most insidious effect of all is on the spacecraft's ability to know where it is and to talk about it. The navigation systems that rely on tracking the subtle shifts in radio signals from distant quasars can be thrown into disarray when those signals have to pass through a turbulent region of space weather. The plasma of the solar wind can bend and scatter radio waves, causing a phenomenon known as scintillation, which introduces errors into the precise measurements needed for interplanetary navigation. It's like trying to see the stars clearly from the bottom of a swimming pool. The image wavers and distorts. Communication suffers a similar fate. A burst of solar activity can cause intense radio noise that drowns out the faint signal from a distant spacecraft, or it can cause the signal to fade in and out unpredictably. During these periods, the already tenuous link to Earth can be severed for hours or even days at a time, plunging the crew into an even deeper isolation and cutting off their access to vital updates and support. The void, therefore, is not a passive emptiness. It is filled with an invisible, dynamic, and often hostile weather system that demands constant respect and a sophisticated understanding to navigate safely. Given that every moment in the void is a high-stakes test of both human and machine, the question becomes how we can possibly prepare for such a multifaceted and unpredictable environment. The answer lies not in the stars themselves, but in a series of carefully constructed simulations here on Earth, designed to replicate the immense pressures of deep space within the controlled safety of our own planet. These analog missions are the crucibles where theory meets reality, where astronauts and mission planners confront potential disasters in a setting where failure is not just an option, but a vital part of the learning process. By voluntarily stepping into these terrestrial voids, we can gather the priceless data and experience needed to avert tragedy when the real journey begins. Among the most sophisticated of these Earth-bound stand-ins for space is NASA, a Human Exploration Research Analog, or HERA. Located at Johnson Space Center, HERA is a compact two-story habitat that is anything but spacious. For up to 45 days at a time, a crew of 4 volunteers is sealed inside this metal capsule, completely cut off from the outside world. The doors are locked, the windows are covered, and communication with mission control is intentionally delayed to mimic the lag a crew would experience on their way to Mars. This isn't a comfortable retreat. It's a psychological and operational pressure cooker designed to simulate the two most persistent enemies of deep space travel: confinement and isolation. Within these walls, every aspect of the crew's life is monitored. Their sleep patterns, their vital signs, their social interactions, and even their saliva are constantly analyzed to understand the physiological and mental toll of their simulated mission. They follow a regimented schedule of scientific research, equipment maintenance, and simulated flight operations, all while dealing with the kind of mundane irritations that become magnified in close quarters. The way someone chews their food, the limited menu of rehydrated meals, the total lack of personal privacy. The true value of HERA and facilities like it is their ability to safely stage emergencies that would be catastrophic in reality. Mission controllers deliberately introduce what they call injects sudden, unexpected system failures that test the crew's resilience and problem-solving skills. A simulated leak might depressurize a module, triggering alarms and forcing the crew into their spacesuits. A critical computer might appear to fail, requiring them to switch to backups and manually reroute systems. The life support system could signal a dangerous rise in carbon dioxide, demanding they figure out a repair with only the tools and spare parts they have on hand. These are not simple drills, they are complex, cascading crises designed to create the same high-stress, high-stakes environment of a real emergency, but with a safety net. If the crew becomes overwhelmed or makes a mistake, the simulation can be paused and the controllers can step in to debrief, analyze what went wrong, and help them develop a better strategy. This process turns potential future failures into powerful lessons, building a library of proven responses and fostering a crew's confidence in their ability to handle the unknown. The training extends beyond technological failures to the intricate dynamics of human relationships under pressure. Psychologists observe how teams handle conflict, make group decisions, and support a member who might be showing signs of fatigue or irritability. They can experiment with different leadership styles and communication protocols to see which are most effective for maintaining cohesion over long durations. This research is invaluable because it provides concrete data on the human element of spaceflight, which is often the most unpredictable variable. The lessons learned in these steel cans directly influence everything from how astronauts are selected and paired together to the design of future spacecraft, ensuring that habitats include private quarters for respite and that work schedules build in time for rest and personal connection. By creating a convincing illusion of the void on Earth, we are able to deconstruct its dangers piece by piece, transforming the terrifying unknown into a manageable set of challenges with practiced, proven solutions, ensuring that when humans finally venture into the true emptiness, they do so not as naive pioneers, but as seasoned veterans of a journey they have already successfully completed many times before. Yet for all the dangers we can predict and simulate, the void holds one final, deeply unsettling wildcard, a threat born not from physics or psychology, but from the fundamental nature of life itself. We have long imagined space as sterile, a cosmic clean room where the only biological entities are the ones we bring with us. But this assumption, while comforting, may be dangerously naive. The possibility, however remote, that we are not alone in the universe extends even to the microscopic level, raising the specter of encountering biological material unlike anything we have ever known. This isn't about little green men. It's about the potential for alien microorganisms, viruses, or prions, unknown pathogens that have evolved in complete isolation for billions of years, following a biochemical rulebook we haven't even begun to read. Consider the environments within our own solar system that were once written off as completely lifeless. We now know that Mars had a warmer, wetter past with conditions potentially suitable for life. The subsurface oceans of moons like Europa and Enceladus are now considered prime candidates in the search for extraterrestrial biology, heated by the gravitational tug of war of their giant parent planets. While the vast emptiness between these worlds seems an impossible place for life to exist or propagate, we cannot rule out the chance that material ejected from these bodies by asteroid impacts could be drifting through space. A spacecraft on a long journey could, through sheer incredible misfortune, pass through a cloud of microscopic particles that originated from such a world. The notion seems like science fiction, but the principle of planetary protection is built on taking this very risk seriously. It is a sobering thought that the greatest biological danger in the void might not be what we bring with us, but what we might accidentally bring back. The risks of such an encounter are twofold, and both scenarios are the stuff of epidemiological nightmares. The first is forward contamination, the chance that our spacecraft, teeming with Earth's hardy extremophile bacteria, could inadvertently infect a pristine alien world. This would be a scientific tragedy of unparalleled scale, forever erasing the chance to study an independent genesis of life and potentially driving any native organisms to extinction through competition or disease. The second and far more terrifying risk is back contamination, An unknown microorganism, harmless in its native environment, could find the warm, wet, nutrient-rich interior of a spacecraft or a human body to be the perfect breeding ground. Because it evolved on a separate world, our immune systems would have zero natural defense against it. It could be utterly benign, or it could be a perfect predator. There would be no antibodies, no known treatments, and no way to predict its behavior. A single spore clinging to the exterior of a return capsule could unleash an unstoppable pandemic upon a completely vulnerable Earth. This is not a theoretical exercise. It is a concrete discipline with rigorous protocols. Every spacecraft destined to land on another celestial body undergoes an obsessive level of sterilization, baked in clean rooms and assembled by technicians in head-to-toe bunny suits to minimize biological hitchhikers. For missions that intend to return samples to Earth, the containment plans are even more extreme. The proposed Mars sample return mission, for instance, envisions a multi-layered strategy worthy of a thriller. The samples would first be sealed within multiple containers on the surface of Mars. The vessel that brings them to Earth would not land. Instead, it would enter orbit around our planet and release the heavily shielded sample container, which would then parachute to a precise landing site. This container would not be opened in a standard lab. It would be transported to a specially built biosafety level 4 facility, the highest containment level possible, the kind used to study the world's most deadly viruses like Ebola. There, inside a negative pressure chamber with scientists working through sealed gloves, the samples would be carefully analyzed for any sign of biological activity before ever being exposed to Earth's biosphere. This meticulous, almost paranoid process is not an overreaction. It is the acknowledgement that the emptiness of space is not truly empty of potential, and that our responsibility as explorers extends beyond our own safety to the protection of our entire planetary home. But as we venture into this new frontier, a critical question emerges from the legal and diplomatic world back on Earth. Who is accountable when things go wrong in the nothingness? The vast emptiness of space is not a lawless free-for-all. It is governed by a complex and in many ways archaic web of international treaties and agreements that were drafted long before the current era of commercial spaceflight and ambitious plans for interplanetary travel. The cornerstone of this framework is the Outer Space Treaty of 1967, a document born from the Cold War that surprisingly remains the closest thing we have to a constitution for space. This treaty establishes that space is the province of all mankind, meaning no nation can claim sovereignty over the moon or any other celestial body. It also places ultimate responsibility squarely on the shoulders of nation-states. If a private company based in the United States launches a spacecraft that malfunctions and crashes into a Russian satellite in the void, the United States government is internationally liable for the damages. This principle of state responsibility means that governments must authorize and continually supervise the activities of all their non-governmental entities in space, a daunting regulatory task as the number of private players skyrockets. This liability becomes incredibly complex when an accident occurs in the deep void, far from any jurisdiction. The current legal framework is primarily designed for events in Earth orbit, where determining fault and assigning compensation for, say, a collision between two satellites follows a set of established, though often contentious, procedures. But imagine a scenario where a spacecraft on its way to Mars suffers a catastrophic failure, and the multinational crew is lost in the interplanetary void. Which nation's laws apply to the investigation? Who determines if negligence was involved? The vessel might be registered in one country, built by a consortium of companies from several others, and carrying astronauts from across the globe. There is no deep space police force, no interstellar coroner, and no agreed-upon protocol for conducting an inquest millions of miles from home. The tragedy would trigger a diplomatic and legal crisis of unprecedented scale, with grieving nations potentially clashing over the cause and blame, all while operating under a treaty that was never designed to handle such a remote and complex disaster. This legal ambiguity extends to the very purpose of exploration and the potential for conflict. The Outer Space Treaty prohibits the placement of nuclear weapons in orbit, but is vague on other forms of militarization. As nations and companies set their sights on the mineral resources of asteroids or the lunar surface, the question of who can extract what and for whose benefit remains largely unanswered. While the United States has passed national laws allowing its companies to claim resources they extract, this is not universally recognized under international law. A dispute between two mining drones over a platinum-rich asteroid in the void would have no clear legal resolution mechanism. There is no court with clear jurisdiction, and the communication delays would make real-time negotiation or arbitration from Earth practically impossible. This could lead to a dangerous escalation where a corporate or national asset takes matters into its own hands, potentially creating a flashpoint that reverberates back on Earth. The emptiness of space, rather than being a unifying endeavor, could become a new theater for terrestrial rivalries, precisely because the rules of the road are so ill-defined for the long and perilous journey through it. While we grapple with the complex legal and biological realities of deep space, our collective imagination has already been there for decades, painted in the vivid and often terrifying colors of popular media. The way most of us understand the dangers of the void doesn't come from scientific journals or NASA briefings. It comes from the silver screen and the evening news. This curated perception, a blend of thrilling spectacle and sensationalized disaster, creates a powerful but often misleading narrative that directly influences public support for real-world space exploration, funding for scientific research, and even the career choices of the next generation. Consider the classic tropes of science fiction cinema. How often have we seen a spaceship struck by a meteor shower, resulting in a single, perfectly round hole in the hull that immediately triggers a violent, shrieking decompression? While the visual is dramatic and heightens tension, it's a far cry from the reality. In the true vacuum of space, a micrometeoroid puncture would be a near-silent event. The hole might be microscopic, and the leak would be a slow, silent hiss rather than a catastrophic explosion. The immediate danger wouldn't be people being sucked out into space. It would be the slow, insidious drop in pressure that could take hours to become critical, a problem of chemistry and engineering, not of explosive force. Similarly, films often depict asteroid fields as dense, chaotic maelstroms requiring frantic piloting to navigate. The reality, as evidenced by the asteroid belt in our own solar system, is a volume of space so vast that the average distance between objects is over 1 million miles. Flying through it blindly would be statistically safer than crossing a busy street on Earth. These dramatizations are not flaws in the films. They are necessary tools for storytelling. But they create a deeply ingrained public expectation that space is a place of constant, audible, and visually obvious peril, which real astronauts must then patiently explain is not quite the case. The news media contributes to this perception gap in a different, more insidious way. Their coverage of spaceflight often falls into a predictable pattern: quiet neglect during years of successful, routine missions, followed by intense, wall-to-wall scrutiny the moment something goes wrong. The phrases explosion and catastrophic failure dominate headlines, while the thousands of hours of flawless operation that preceded the accident are forgotten. This creates a powerful availability heuristic in the public mind. The most easily recalled examples of space travel are its disasters. The Challenger and Columbia tragedies are cultural touchstones, their imagery seared into public memory. The countless successful shuttle missions, the ongoing, miraculous 20-year operation of the International Space Station, the flawless landing of the Perseverance rover on Mars, these are footnotes by comparison. This skewed coverage fuels a perception that spaceflight is inherently and unacceptably risky, a game of Russian roulette where failure is the norm rather than the rare and devastating exception it truly is. It ignores the meticulous culture of safety, the endless testing, and the layers of redundancy that define modern aerospace engineering, instead presenting a narrative of brave but foolhardy adventurers tempting fate. This gap between perception and reality has tangible consequences. Public opinion, shaped by these dramatic portrayals, directly translates into political will and funding. A citizenry that believes space travel is a death-defying stunt for daredevils is less likely to support government budgets that allocate billions to NASA or other space agencies. They may see it as a wasteful risk, a dangerous vanity project, rather than a strategic investment in science, technology, and the long-term future of humanity. This perception can stifle ambition, causing mission planners to become overly conservative, avoiding bold but necessary steps forward for fear of public backlash should anything go wrong. Conversely, the media's ability to inspire cannot be ignored. The breathtaking footage from the Hubble and Webb space telescopes, the live stream of a rover landing on another world, the awe-inspiring sight of a rocket landing itself on a drone ship, these moments of wonder cut through the noise of disaster and capture the public's imagination. They create a counter-narrative of capability, precision, and glorious discovery, demonstrating that the void is not just a place of danger, but a frontier of infinite promise. The challenge, then, is not to ignore the risks, but to present a more complete and honest picture, one that acknowledges the very real perils we have outlined throughout this video, while also celebrating the profound human achievement of learning to navigate them with intelligence, courage, and care. So after this long and sobering journey through the myriad dangers of the void, from the invisible rain of radiation to the profound psychological toll of absolute isolation, we are left with the ultimate and most difficult question of all. Given the staggering costs, the existential risks, and the very real possibility of tragic failure, is it truly worth it? Should humanity continue to push its fragile bubble of life into that infinite, hostile darkness? The answer is not a simple yes or no, but a deep and necessary tension between two powerful and fundamental human drives, the instinct for survival and the imperative for discovery. On one side of the scale, we must place the sobering realities. The risks are not abstract, they are concrete and catastrophic. We are talking about the potential loss of human lives in the most terrifying and lonely way imaginable, an event that would reverberate through generations. We are talking about the diversion of vast sums of public money, funds that could be used to solve pressing problems here on Earth, from disease and poverty to climate change. There is a compelling argument to be made that we must fix our own planet, our one and only certain home, before we gamble our resources and our people on such a perilous and uncertain endeavor. This is the voice of caution, of responsibility, and it demands to be heard. It asks us to consider whether this drive to explore is a noble calling or a dangerous hubris, a modern-day Icarus flying too close to a sun we cannot hope to tame. Yet, on the other side of that scale lies something equally powerful, the undeniable and ancient human spirit of exploration. This is the same drive that sent Polynesian voyagers across the trackless Pacific in outrigger canoes, that propelled Magellan's ships over the edge of the known world, and that compelled Armstrong to take that first step onto the lunar dust. To turn away from the void now would be to deny a fundamental part of what makes us who we are. The potential discoveries are not just scientific curiosities, they are keys to understanding our very existence. Venturing into deep space could answer questions we have not even learned to ask yet. It could reveal the secrets of the universe's birth, the nature of dark matter and dark energy, and perhaps even the potential for life elsewhere. The technological spin-offs from this immense challenge have historically revolutionized life on Earth, leading to breakthroughs in medicine, computing, materials science, and environmental systems. The pursuit itself forces us to become better, smarter, and more collaborative as a species, forging international partnerships and driving innovation at a pace rarely seen in human history. Perhaps the most profound argument for pressing on is one of long-term survival. All of our eggs are, for now, in one planetary basket. History shows us that extinction-level events are not a matter of if, but when. An asteroid impact, a supervolcano, or a planet-wide plague could end the human story in a geological instant. By learning to live and thrive in the void, by establishing a presence on other worlds, we are not abandoning Earth. We are acting as its responsible guardians, ensuring that the light of human consciousness is not so easily snuffed out. This is the ultimate backup plan for humanity, a way to secure a future that is not dependent on the continued and fragile stability of a single world. The void is the most dangerous environment we will ever face, but in confronting that danger, we may just secure our place in the cosmos for millennia to come. The journey will be the hardest thing we have ever done, but the reward is nothing less than a future for humanity itself. The emptiness of space is not a void to be conquered, but a profound reality to be understood and respected. It is a realm that demands not just courage, but an unwavering commitment to preparation, innovation, and collaboration. Our journey through these hidden dangers reveals a simple, powerful truth. The greatest challenge of exploration is not the distance we must travel, but the wisdom we must cultivate to survive it. The void does not forgive arrogance or oversight. It rewards humility, meticulous planning, and a deep reverence for the complex physics that govern every inch of the cosmos. From the silent, subatomic chaos of quantum foam to the immense gravitational tides of dark matter, the universe is alive with forces that test the very limits of our ingenuity. This is not a reason to retreat, but a call to evolve. The knowledge we gain from confronting these perils does more than just enable safer spaceflight. It fundamentally expands our understanding of our place in the universe. Each solution engineered to block radiation, each protocol developed to sustain a crew's mental health, and every international treaty drafted to ensure peaceful exploration adds another layer to our collective resilience. We are learning to build not just spacecraft but arcs, self-sustaining fragments of our world capable of enduring an environment that was never meant for us. This endeavor pushes the boundaries of science, medicine, and human potential, creating a legacy of technology and knowledge that benefits all of humanity, even those of us who remain firmly on the ground. So as we look up at the star-filled night sky, let's see it not as a dark and empty unknown, but as the next great ocean, a vast frontier filled with both immense challenge and infinite promise. The journey ahead will be our species' greatest testament to curiosity, courage, and cooperation. Thank you for exploring the depths of this mystery with us. If this journey into the cosmos sparked your curiosity, feel free to subscribe for more adventures into the unknown, and let us know in the comments which cosmic mystery we should investigate.